We now want to talk about Coulomb's law in a little bit more detail, and as we're doing so, we need to introduce what the charge and the mass on the proton, electron, and neutron are. And to answer the first question about the charge, the electron and proton both have the same magnitude of charge, 1.6 times 10 to the negative 19 coulombs. Now that may seem like a really odd number, and in many ways it is, but this is an artifact of the fact that the coulomb was defined well before the size of an individual charge was known. And the Coulomb was actually defined in terms of electric current, and we will discover that in a few chapters. But for the moment, this is what we're stuck with. Okay, so it's a little esoteric, if not somewhat clumsy, but it's what we're stuck with in the nomenclature. So the magnitude of an individual charge is 1.6 times 10 to the negative 19 coulombs. And the electron has a negative sign since it's a negative charge, and the proton has a positive sign. The neutron is not charged, so it has a total charge of 0. Now, in terms of mass, right, how large are these particles? Well, they're not very big at all, okay? And it turns out that the electron is by far the smallest out of the three. And these are, by the way, the particles that make up atoms. Okay, these are the particles that make up atoms. So these are subatomic particles, but they're not the most fundamental of particles, right? So they're not fundamental in the sense the way things like quarks are, if you've ever heard of a quark. But these are the most common type of atomic particles, and they occur most often in nature. And so these are the particles that we're going to study in most detail here. Now, the electron is extremely small in mass, 9.1 times 10 to the negative 31 kilograms, okay? Very, very small. Now, the proton and the neutron, according to this table, have the same mass. If we were to extend those decimal places out, you would find that the neutron is just ever so slightly larger than the proton, but they're both roughly 1.67 times 10 to the negative 27 kilograms. Still extremely small, but still much larger in terms of mass than the individual electron. Okay, now we've said that one individual charge has a magnitude of 1.6 times 10 to the negative 19 coulombs. So if I have 1 coulomb of charge, if I have a collection of charges that is equivalent to 1 coulomb, how many charges do I have? So to answer that question, we can simply take the reciprocal of 1.6 times 10 to the negative 19, and in doing so, we see that there would be 6.3 times 10 to the 18 individual charges. That would then make up a coulomb of charge. So if I have 6.3 times 10 to the 18 protons all collected together, then that would be 1 coulomb of charge. Now that is an extraordinary amount of charge, okay? Most objects that you are going to run into are nowhere near that charge. They are usually thousands, if not millions of times less charged than that. So that is an extraordinary amount of charge. And in fact, if you were to take a metal sphere and place 1 coulomb of charge on it, you would not want to be in the same room as that charge. That would be enough for the electrostatic forces from those protons to more or less tear your body apart, which would not be a very good time at all. So it is a very large amount of charge, and again, it's a consequence of the fact that amperage was defined first, and then the coulomb was defined from amperage, and nobody really knew at the time when those things were being defined just how small these individual charges are. So those are why the numbers, the individual charge themselves is a really small number, and why there's such a large number of charges in a given coulomb. Now, you've probably heard that opposite charges attract and like charges repel, and that is true. So suppose I have a collection of 2 charges, 2 protons, say, the figure on the left, and we can call one of the charges Q1, and we'll call the other charge Q2. And these 2 charges are going to repel each other. So if I look at the blue arrow off of Q2, it says F12. And what this means is that this is the force that charge 1 exerts on charge 2. So that's what the nomenclature F12 means. The force that charge 1 exerts on F2, or Q2. The force that charge 1 exerts on charge 2. And as you can see, it's going to repel away, directly away from Q1. And the same thing is going to hold for Q1, right? Q1 is going to feel a force from Q2. If they're both charged, they're going to feel equal and opposite forces. And so it is also going to feel a force equal in magnitude, but also opposite in direction. So the F21 would be the force that charge 2 exerts on charge 1. And the forces are going to be oppositely directed or oriented, right? Now, what if our charges are of different sign, right? What if we have opposite signs? Well, in this case, the force is going to be attractive. So suppose I have a proton and an electron, then the force is going to be attractive, and F12 would represent the force that the proton exerts on the electron, and F21 would represent the force that the electron exerts on the proton. Now, there's one scenario here that's missing explicitly, but it's implicitly implied because we have two protons, a proton and an electron, and you may be asking, well, what would happen if I have two electrons? And the answer is the diagram would be exactly the same as the two protons. The charges are going to repel each other, and the forces are going to be equal and opposite as well. Okay, so that is how the charges are going to interact. And the forces are always going to be directed along the line joining the two charges, right? The shortest line joining the two charges, or the axis that you can draw between the two charges, the force between 2 point charges is always going to lie directly on that line. So, quick thought question here. What if object A has a charge of 2 microcoulombs and object B has a charge of 6 microcoulombs? Which statement is going to be true? Are the forces going to be oppositely directed, but one of the forces 3 times as large, since the ratio of the charges is 3? Are they going to be equal and opposite? Or are they going to be the exact opposite of the first scenario, where they are opposite in sign, but now this time the original force is 3 times as large? And just a quick thought would lead you to Newton's third law. For every force, there's an equal and opposite force. So it actually does not matter what the ratio of the two charges are. They do not need to be the same magnitude in charge. The forces will still be the same, okay? The forces will still be the same. And we can see that if we now go to Coulomb's law, right? If we now go to Coulomb's law, so if I want to calculate the force F on, let's say, on Q1, so let's come back up here, right? And let's call this Q1, and we'll call this Q2, and I want to calculate what this force F21 is, okay? Well, Coulomb's law says that the force on charge 1 is going to be equal to Coulomb's constant times charge 1 times charge 2 divided by the distance between them squared. But if I come back up here and I want to calculate F12, the magnitude of F12, then it's just the same thing. It's going to be the product of the charges times Coulomb's constant divided by the square of the distance between them. So it doesn't matter if your charges have different magnitudes of charge. The same numbers will get plugged into the force regardless of which one you're calculating, the force on the first charge or the force on the second charge. So Newton's third law holds ubiquitously for Coulomb's law, but it's up to you to then supply the direction. Now, before we move on, let's look at Coulomb's law and draw a couple of parallels here with Newton's universal law of gravitation. Okay. First things first, they both describe forces, and one of the first things you'll notice is that they both depend on r squared. They're both what we call an r squared law, okay? So what this means is that both forces depend on the square of the distance between my objects, whether they're interacting gravitationally or whether they're interacting electrically. And the force is inversely proportional to this r squared factor. So what this means is, as I bring my objects closer together in both cases, the force is going to get much stronger. And as I separate my objects, as I make r very large, the force is going to decrease. It's going to get much smaller. But there's more similarities here. First things first, notice that in Coulomb's law we have Ke, and in Newton's universal law of gravitation we have the constant G, and both of these just represent constants. Now these are both constants of nature. One is a gravitational constant, one is an electric constant, but they're both at the end of the day just a proportionality constant. And then what's left, we have the product of the masses in the law of gravity, and we have the product of the charges in Coulomb's law. And this is extremely similar because the mass of an object is an inherent property of that object. So if I have two objects, M1 and M2, the product of those masses is also an inherent property of the system, right? So the product of M1 and M2 is going to be an inherent property of my gravitational system. Likewise, if I have two, and by the way, so as long as those objects are isolated in space, that will never change. M1 and M2 will stay fixed for all time. That's why I call them an inherent property. Same thing with Q1 and Q2. If Q1 and Q2 do not interact with anything else, once an object is charged, if it does not interact in a way that draws charge off of its surface, it will stay charged for all time. So the amount of charge on my two objects or my two particles is also an inherent property. So both laws have the form where we have a constant multiplied by the product of a property that's inherent in the system, in one case charge and in another case mass, and then divided by the square of the distance between them. So they both follow the r squared law, the inverse square law, if you will. And so there's a remarkable symmetry here that actually took physicists quite by surprise. And another reason why this is a little surprising, Newton's universal law of gravitation was initially derived mathematically, theoretically by Isaac Newton, whereas Coulomb's law was found experimentally. And for one to be found with pure mathematics, and the other to be found with experimentation, and they both have this deep symmetry between them, was quite remarkable. So that's a little bit about Coulomb's law, and in the PowerPoint you'll notice that there are a couple of examples on how to actually use Coulomb's law, and in the next video we will start to explore electric fields. So we will see you then.